Welcome to The Explainer. We're surrounded by these incredible natural forces every single day. The wind carving out canyons, the tides pulling entire oceans. We kind of think we've got them figured out. But what if there's a single, super simple principle driving both of them that's been hiding in plain sight this whole time? Okay, just hear me out on this one. It sounds weird, I know. But what if a simple bicycle tube could help us understand the massive engine that powers our planet's atmosphere? You gotta stick with me, because this is where it gets really, really interesting.
All right, so section 1, we all learn in school, right? Wind is about temperature. Hot air goes up, cool air sinks down. Simple. But, as we're about to find out, that's not the whole story. There's a crucial piece of the puzzle missing, one that changes everything.
So let's do a little thought experiment. We take that bike tube, we fill it with air, and we lay it perfectly flat. Now, let's say we warm up one side and cool down the other. We've got our temperature difference, right? The warm air gets lighter, the cool air gets heavier, and they just separate. They form layers. But look, nothing is actually moving. There is zero circulation, no wind.
So what gives? Here's the puzzle. We have the exact thing we thought causes wind, hot and cold air, next to each other, but everything is just sitting there. It's perfectly layered, sure, but totally static. Why? What are we missing here?
And here it is, the aha moment. We take that exact same tube, we don't change the temperature at all, we just do one tiny thing. We tilt it, and bam. Instantly, a current starts. Gravity gets a hold of that cold, dense air and pulls it straight down. And as it falls, it literally shoves the lighter, warmer air up the other side. You get this continuous loop, you get wind. So you see, the only thing that changed was its position in space. When the tube was flat, there was no up or down for gravity to work with. No height difference, no circulation. But the second we tilted it, we introduced height. And that gave gravity the leverage it needed to kickstart the whole engine. That tilt, that was the secret ingredient. So it turns out you don't just need one thing for wind. You need a trio. You need a temperature difference, yep, that creates the different densities. You need gravity, of course, to pull on those densities. But the trigger, the thing that makes it all go, is a height difference, high and low. Without that, nothing happens. Now here's the really cool part. This incredibly simple idea we just saw in a bike tube, well, we can scale it up to understand the winds across our entire planet. Let's just picture two different worlds for a second. First, think about Jupiter's moon, Europa. It's got an atmosphere, but its surface is unbelievably flat. And guess what? There's practically no wind there. Now think about Earth. Our huge mountains and deep valleys, they're basically our planet's version of tilting the tube. They create the massive height differences that let gravity drive our enormous global wind patterns. And the source material for this explainer just says it so clearly. A planet that's totally flat would barely have any wind to speak of. It's the bumps and ridges, the topography of the planet itself, that actually unleashes the power of the atmosphere. Okay, so we've seen how this natural circulation works for wind, but now let's shift gears and look at our oceans. Could there be a similar hidden force at play, helping to power the massive tides? I mean, we all know the classic story for tides. It's the gravitational pull from the sun and the moon. But this idea of temperature and position driving movement is, well, it's pretty powerful. So you have to wonder, does it also work for water? Get ready for this, because this fact is kind of a showstopper. The sheer amount of heat energy the sun blasts into our oceans every day is many, many times greater than the gravitational pull from the moon. So that just begs the question, could all that heat be physically moving the water? And it works exactly like our bike tube. Think about it. On the side of the Earth facing the sun, the ocean gets warmer and that water becomes a little bit lighter. On the night side, it's the opposite. The water cools down, gets denser, heavier. And so that cold, dense water sinks. And as it sinks, it physically pushes the warmer water on the other side of the planet, creating this huge daily shift of water across the entire globe. So let's put this all together. This gives us a completely new way to look at the daily rhythm of the tides. We're not throwing out the old ideas. We're adding a powerful new force to the mix. And there's a name for this. It's called thermal displacement, and it's the exact same principle we saw with the wind. just in water. Colder, heavier stuff sinks because of gravity, and it literally shoves the warmer, lighter stuff out of the way. It's a simple mechanical push, happening on a planetary scale.
So what this new perspective suggests is that tides aren't just about gravity. They're actually the result of two massive forces working together. You've got force number one, the one we all know, the gravitational pull of the sun and moon. And then you have force number two, the hidden one, this enormous push from solar thermal displacement.
And that right there, that brings us to this really beautiful, unified idea at the heart of this whole thing. Whether we're talking about the air moving on our planet or the water moving in our oceans, it seems like they're both powered by the same elegant engine, natural circulation, driven by the simple dance between temperature, gravity, and position.
It's a pretty wild thought, isn't it? That the key to understanding some of the biggest forces on our planet might be as simple as just tilting a tube. And it really makes you wonder, what other giant forces of nature are out there, just waiting for us to finally spot their simple secret ingredient?